Hello and welcome to this lecture. So, we've already seen least square solution to linear equations, but sometimes you may wonder what is going on, right? So there seems to be a lot of underlying things that are happening here, and what we're going to see next is some background and slightly more abstract view of what we did just now with least square solutions. And to do all that, this notion of an orthogonal complement is very, very useful. So, let's define this orthogonal complement. You saw one thing that was very crucial in the least square solution was this one vector, the special vector v minus w star, which ended up being orthogonal to every vector in the subspace, right? So, we are going to use that idea and define this notion of an orthogonal complement. So, that is where it comes from. Notice this. So, you have this Fn and you have the subspace S, and the orthogonal complement of a subspace S denoted S perp. Okay, so this is my notation, it is called S perp, is the set of all vectors in Fn which are orthogonal to all vectors in S. All these these projections, the perpendicular lines that we had before, this v minus w star type guys, you collect all of them together, you form this S perp. So, they have to be orthogonal to every vector in S. Okay. So, that is what this definition tells you. This w, as w goes through S and you have this u should be orthogonal to everything. I mean, I am not projecting from here, remember, this u needs to be orthogonal to everything in W, then this u will belong to S perp. Okay, so this is my sort of related to that previous least squares problem. You see where it comes from. Why are they interesting? So, because if W star is in S, right, if you have, so W star in S is closest to V, then this V minus W star is in S perp. So, this S perp is interesting because these V minus W star guys have to belong to S perp, and if you understand S perp, maybe we can do something, or we can find something out clever which is at the background of all these least squares problems. Okay. So, this is one reason. Here are a couple of nice properties about this S perp. This S perp has a lot of structure to it. First of all, this S perp is a subspace. Okay, so you can see this very easily. The proof is very easy. If u and u2 are in S perp, then for any w in S, look at this inner product. au1 plus bu2 comma w, the inner product, is using the linearity of inner product. The first argument a u1w plus b u2w. But u1 and u2 are in S perp, which means what? u1w and u2w are both 0, right? Because w is in S. So, this will end up being 0. So, any linear combination of u and u2 also shares that property that it is orthogonal to every w in S. So, you have a u1 plus b u2 also belongs to S perp. So, S perp is a subspace. Okay. So, this S perp's orthogonal complement is not any old set, it is actually a subspace, right. So, we are learning more about this S perp. Here is another one. S and S perp have only the origin in common. There cannot be any non-zero vector that is common to both S and S perp. Okay. So, that is the interesting little fact here. So, this result is also very, very curious. Okay. How do you prove it? It is very easy. If u is in S and u is in S perp, supposing you have a vector in this intersection, it is in both S as well as S perp. This is intersection, right? What is intersection? The vectors that are in both S and S perp, right? That can only be origin I am claiming. So, supposing there is a u, I have to show that this u is 0, right? So, what happens now? U is in S, u is in S perp, which means u comma u has to be 0. The inner product u comma u has to be 0, right? U is in S, u is in S perp. Now, what do we know? Only vector that satisfies this is u equals 0. Okay. So, this intersection is only 0. Okay. So, this understanding of S perp, this simple little understanding of S perp is enough for us to show that the W star is unique. Okay. So, that is what we are going to show, uniqueness of the closest vector, right. So, this was a problem. We had an Fn, we had a subspace S and vector v which is outside of the subspace, let us say, right, and then this W star is closest to v in the subspace, right. So, this is my argument minimization, this is the least squares as 2 norm or the squared error distance, squared distance, and what do we know about this W star? V minus W star belongs to S perp, right, we know that already, and this S perp is a subspace, we know that, and S perp has nothing in common with S except for 0, that also we know. Okay. Now, armed with this facts, we can show W star is unique. Let us show W star is unique. Okay, here is the proof. Suppose there are 2. Okay, so this is how these uniqueness proofs mostly go. You assume the opposite. You assume there are 2 and then show the 2 has to be equal. Okay, so that is what we are going to do also. By contradiction, we will prove it. Okay, some sort of contradiction. So, if there are 2, here is the structure that is coming out. Both of them belong to S, right? Of course, they belong to S. W star belongs to S, right? So, both of them will belong to S if there are 2 optimum values. And these 2 guys have to belong to S perp. What are the 2 guys? V minus W1 star and V minus W2 star both have to belong to S perp. Okay, this also is true, right? So, because we know that this is true for this minimizer. Okay. Notice what happens if W1 star and W star in S, then W2 star minus W1 star has to be in S, right? If you subtract these two, they have to be in S, right? Now, these two are in S. Now, again, the difference of these two will also be in S perp, right? These two are in S perp, I am sorry, V minus W1 star, V minus W2 star and S perp. So, if I subtract these two, that also has to be in S perp, but then the difference here V will cancel and you will get only W2 star minus W1 star. So, this wonderful little vector W2 star minus W1 star has to be in S, it also has to be in S perp. Now, is that possible? That's possible, except that W2 star minus W1 star has to be equal to 0, which means W2 star equals W1 star. Okay, so this shows you that this W star will be unique. So, if you sort of project from V to a subspace, the subspace is important. If you project from V to a subspace, it will result in only one W star such that V minus W star is perpendicular to all vectors in the subspace. Okay, the subspace property is important, and that is where you get the uniqueness. Okay, so the uniqueness proof is also done. Okay, so now we are going to define something called a projection operator. Okay, so now that we know this W star is unique, we can define a projection operator. Okay, so how does that work? So here once again I have the same situation. I have a unique W star which is closest to V. I can define my operator from F1 on to S, but of course the operator is from Fn to Fn, right? But its range is only S, or it takes only values in S. I will denote it as PS. Okay, the operator is denoted PS, meaning projection onto S. That's what it means. Projection onto S is basically defined as the mapping from any V to W star. Okay, so I know this W star is unique, right? So I take any vector V in Fn. What do? I have this subspace S defined. I will simply project to subspace. Whatever W star I get, I will give as output of my projection operator. It's well defined by the uniqueness. I won't get ambiguous values. There will be only one W star that I will get. That's defined very well by the uniqueness property. Is that okay? So, this is the definition of the projection operator. Okay, I have defined an operator. You can see very easily that the range of the operator is S and all that, and all of these things you can see. And for every V, it's defined. Don't worry about V being inside S. If V is inside S, the output is itself, right? You will get the same answer, right? So, it's very well defined for every V in Fn, and that's the projection operator. Here is a very interesting property. This projection operator is a linear operator. Okay, so notice it's coming out of the solution of some non-linear problem in some sense, right? The squared error distance, there is a square and all here, but still this W star is a V to W star is a linear operator. Again, the orthogonality condition is what is very, very critical. We'll prove this linearity. It's very easy to see. Supposing PS of V1 is W1 star and PS of V2 is W2 star. There are V1 and V2 that satisfy this condition. Then what do I know? V1 minus W1 star is in S perp. V2 minus W2 star is also in S perp. So, notice what happens. If I do A times V1 minus W1 star plus B times V2 minus W2 star, what do I get? I can group these things together. I get AV1 plus BV2 minus AW1 star plus BW1 star. That also now has to belong to S perp, because these two belong to S perp, so this has to belong to S perp. Now, look at this equation. Stare at this equation very closely. AV1 plus BV2 minus AW1 star plus BW1 star is in S perp, and this AW1 star plus BW1 star actually is in S, right? W1 star is in S, W2 star is in S. So, AW1 star plus BW2 star is in S, okay? And this difference is in S perp, which means the projection of AV1 plus BV2 is actually AW1 star plus BW2. Let's think about this a little bit, you will see where it comes from. So, this PS is a linear operator. So, the projection operator is linear, and what we have been doing in the projection is actually do a linear operator on V. Okay, that's what we are doing when we project. Okay, so we've seen the orthogonal complement, we've seen the power of it in figuring out the uniqueness of this W star, and also understanding that the projection operation is nothing but a linear map that we did. In fact, the formula also was a linear map if you think about it, but it's a linear map that we have done. Okay, so now let's think about basis for the orthogonal complement. Now this will help us tremendously in being able to compute the projection very, very easily. Okay, so that's where we are going here. So we need a basis for the orthogonal complement. If you do this, it's very, very interesting, and you can do this. Okay, so let's get started. The idea first is to extend an orthonormal set to an orthonormal basis. Okay, so here is the idea. So if you remember before, we could extend a linearly independent set to a basis for the entire vector space, right? It turns out you can do that even for orthonormal sets. If you have an orthonormal set of vectors, you can extend it into an orthonormal basis for the entire vector space. So that is the fact that's stated here. If you have u1 to uk being an orthonormal set in Fn, then there exists uk plus 1 to un such that the entire n length set u1 to un added with this uk plus 1 to un will be an orthonormal basis of Fn. So all you need to show is that this guy is an orthonormal set. No, that's enough. You have n guys which are orthonormal, they become a basis for Fn. Okay, you can extend any k, keeping the k the same, you can add some more to get an orthonormal basis. So that's a powerful thing. The proof actually uses Gram-Smith process. So here is what we start with. You have your set of orthonormal vectors u1 to uk. You take any basis for Fn, v1 to vn, and you do Gram-Smith on this set v1 to u1 to uk, your original orthonormal set in that sequence, right? You start with that and then simply append the v1 to vn. Now what this v1 to vn appending does is, it makes the span of this entire list equal to Fn. Okay, and then what do? I am employing Gram-Smith. What will Gram-Smith do? At the output I will get a orthonormal set whose span remains the same as Fn, right? So my span will be Fn. Okay, so I will get my basis, right? Now what will happen when you run Gram-Smith? As you keep running Gram-Smith, you see, what do? You take inner products with the waters on the left and keep adding new things, right? You will see that u1 to uk will be output exactly as such because they are already orthonormal. So up to uk you won't change anything. So the same thing will come out, right? If you take orthonormal, see, if you take inner product of uk with everything below before it, it's all 0. So you won't change the uk, your w will become the same as the uk. And normalizing also won't change anything because already it's orthonormal. So you will keep outputting the same thing. You can go back and check the loop there. You will see that loop will output the exact same thing from u1 to uk. But of course from v1 to v, as you go further, it will keep changing. So the next n minus k outputs, you can let it be uk plus 1 to un. Okay, at u1 it will stop, right? After that it will only give out zeros because you cannot have more than n orthonormal vectors. They are all independent. You cannot have more than n. So it will stop at that point. So the next k minus n minus k outputs will be this. So just running Gram-Smith in a clever fashion allows you to prove extension. Okay, so just like elimination helped you in the linear independence case, orthonormal case, Gram-Smith helps you. So once you are armed with this, you can come up with an orthonormal basis for S-perp. Okay, so you define S with an orthonormal basis. How do I find this S-perp, right? What is the basis for it? I know it is a subspace. I know it has only intersection 0 with S, but how do I find a basis for S-perp? Okay, so here is the method. u1 to uk, let it be an orthonormal basis for S now. Okay, so it's not any old orthonormal set, it's a orthonormal basis for the subspace S. Now I know I can extend it to find a basis for Fn, an orthonormal basis for Fn, right? u1 to uk, uk plus 1 to un. It turns out all the remaining fellows that you added, uk plus 1 to un, is an orthonormal basis for S-perp. Okay, so this is a very clean and very nice idea. And when you extend the basis, orthonormal basis, you get a new orthonormal basis. Whatever you added additionally becomes an orthonormal basis for S-perp. Okay, sort of intuitive because all these guys are perpendicular to those fellows, so it's intuitive. But nevertheless, here's the proof. If you have a V in S-perp, right, I should be able to write it down uniquely in terms of this uk plus 1 to un. If I can do it, I can show that, and I'm done, right? So notice this, any V in S can be written uniquely in terms of u1 to un, right? u1 to un is a basis for the entire Fn. So clearly any V in S-perp I can write. But then my V is in S-perp. What does that mean? V comma u1, V comma uk, all the way till all those guys will disappear. They'll all go off to 0. So I'll only have V comma uk plus 1 uk plus 1 all the way to V comma un. So the any V in S-perp can be written uniquely as a linear combination of uk plus 1 to un, and you're done. Okay, so the basis for S-perp is uk plus 1 to un. Okay, so from this come a couple of very, very powerful properties. You would have a subspace of Fn dimension k, and you define an S-perp as set of all vectors which are perpendicular to all vectors in N. The dimension of S-perp is n minus k. Okay, dimension of S is k, dimension of S-perp is n minus k. We just show a proof. Basis of S-perp has n minus k orthonormal vectors, so dimension is n minus k. Okay, here is another very interesting property. The complement of the complement becomes S itself. If you had an S, you did a complement, you went to another subspace S-perp. Of course, I can repeat the complement again, right? But if I do it, I go back to my S. Okay, So, it is equal. There are two things needed here. The vectors in S are clearly orthogonal to everything in S pub. That was definitely the definition. So, S is contained in this orthogonal set in this complement, but then how do we show that they are equal? That just comes from a dimension counting, right. So, dimension of S pub is n minus k, right, has to be k. Now, I know my dimension of S is also k. So, S has to be equal to S pub. Okay. So, there is a little bit of an abstract proof for this complement of orthogonal complement being the original subspace itself. So, these are nice properties of a basis. So, now we know given a subspace S, and if I find an orthonormal basis for it, I can extend it, take the remaining ones, I find an orthonormal basis for the complement. Now, what do I put this to use for? I can use it in projection beautifully. In fact, I can find a matrix for my projection operator. Okay, how do I do that? This is how you go about doing it. Okay, let's say U1 to UK on orthonormal basis for S, and I've extended it to find an orthonormal basis for Fn. Okay, these are all, I'm going to think all of these as column vectors. Okay, keep that in mind. They are all column vectors with respect to the canonical basis. All of these guys are column vectors. They are of course orthonormal. Now, I have a vector V in Fn, which is also a column vector and canonical basis. Think of it that way, because I am thinking matrix. No, I am thinking matrix with respect to a basis. The basis we picked is the canonical basis. Okay. So, if I want to evaluate projection of this V onto this subspace S, how do I do it? I have a basis here. I can write V, I know the answer actually, right. So, this is the first part, but anyway, let me write V as V in terms of this basis, right, the orthonormal basis. So, if you do that, what will happen? The first part is the projection. So, that is Ps of V, right, V comma U1 till V comma UK. Till UK I have the projection. The remaining part I know belongs to S pub, right. So, this is how this splits. This is how I evaluate my projection. This is very standard. Now, if you look at this part here, this is just inner product multiplying vectors, right. I can write this inner product in terms of matrix, right. So, I've thought of U1 and all these guys as column vectors. So, this V comma U1 is U1 Hermitian V, right, U1 Hermitian V multiplying a column vector here plus so on, UK Hermitian V multiplying a column vector UK. This is UK Hermitian, remember, is the row vector with conjugation also. Okay. Now, if you stare very carefully, these guys are scalars, okay, just a number 2, 3, 1 plus j, whatever. This is just a scalar number, and this U1 is a vector, right. So, scalar and vector, I can move the scalar to the other side. Okay, that is a crucial observation. So, I can U1 and then multiply the scalar on the right or the left, it does not make any difference. Okay. But now, I will cleverly use matrix associativity. So, I am multiplying 3 matrices here, U1, U1 Hermitian and V, but the product is associative. So, I can as well write it as U1, U1 Hermitian multiplying V plus so on till UK, UK Hermitian multiplying V. Now, this V is common here, I pull it out, I get U1, U1 Hermitian plus so on till UK, UK Hermitian. What is this U1, U1 Hermitian? U1 is a column vector, U1 Hermitian is a row vector. A column vector of length n, row vector of length n. Column vector multiplying row vector gives you an n cross n matrix, and that is a matrix, right. So, these are all n cross n matrices, n cross n rank 1 matrices as it turns out. Okay. Why are they rank 1? Think about it. If every column is a multiple of the first column, right, U1 times U1 Hermitian. So, that kind of a product is called an outer product. It is a rank 1 matrix. So, a bunch of k rank 1 matrices are being added to get this matrix here. So, this defines the matrix of PS. So, notice PS of V has been written as a n cross n matrix times a vector V. So, this guy is nothing but the matrix of PS with respect to the canonical basis. What is the formula? U1, U1 Hermitian plus so on till UK, UK Hermitian. Okay. So, of course, this extension and orthogonal basis and all was not needed. It is just to drive home the point that this projection is just this and you get this answer. Okay. So, now we know once you have an orthonormal basis for your subspace S, you can find the orthonormal basis of the complement if you want. You can also find the matrix of the projection operator very precisely. Okay. So, properties of projection. This projection operator has a lot of very simple and nice properties. First of all, PSU equals U for U in S. Okay. If you are inside the subspace, the PS does not do anything. If you are in the dual, then PSW is 0. Okay. But if you are neither in S nor in the dual, you are partly here, partly there. Okay. Something in S added to something in S pub, then you will get interesting answers, right. So, otherwise you will get just 0 if you are in S pub fully. The range of PS is S. The projection goes to only the subspace. Null of PS is S pub. okay, and the dimension, everything works out, right? Range is dimension k, null is dimension n minus k, this purpose dimension n minus k, all of that works out very, very precisely. And interestingly, ps square is ps, okay. You can prove this in so many different ways. PS square has to be PS, right? See, if you do PS once, you've gotten into the subspace. You do PS again, you're not going to change. You're going to be staying in the same place. So PS square better be equal to PS. But you can also show using that algebraic expression. I'll leave that as an exercise to you. You take that algebraic expression, right? U1 Hermitian plus so on till UK Hermitian. You multiply it with itself. Use your distribution properties and all that, and you'll see you'll get the same answer. Okay, try it. You'll learn something from that. Okay, so here are a few problems. You can try it. A span of two vectors is given. You have to find an orthonormal basis. Run Gram-Schmidt here. I'm not going to do it for you. Run Gram-Schmidt. Find the U1, U2 as an orthonormal basis for this, and then you can find everything you like, projection operators, etc. Now, here is a more interesting problem. X1 to xn, x1 plus so on till xn equals 0. This is a subspace. This is actually a n minus 1 dimension subspace, right? So this is like a null space equation. My xn is a x1, x2 to xn are free variables. X1 is defined as minus of all these guys. So you have n minus 1 dimension subspace here. Okay. So if you have to find the projection operator, it looks like a complicated problem, but it may have a lot of simple ways to do it also. So try this problem on your own. Look at the basis. The basis may be close to orthonormal. Maybe let me at least get you started on it. What do I mean by that? Let's do that. Okay. So my subspace is set of all x1 to xn such that x1 plus so on till xn equals 0. What is the basis for it? Basis for it is you can pick everything else 0 except for one guy, right? So you want to put 1 0 0 0. This guy will be minus 1. And the next one will be minus 1 0 1 0, so on till the last one minus 1 0 0 dot 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 1. Okay, this is the basis. It's got n minus 1 dimension basis. You have to orthonormalize it. This is not orthonormal, no? So if you take a dot product here, you're getting 1, right? So it's not orthonormal. So is there a clever way in which we can make it orthonormal? You can think about it. Maybe you want to do Gram-Schmidt, etc. But maybe you can think of something slightly more interesting. What if I look at this vector, right? So if I look at this vector, v, which is 1 comma 1 comma, so everywhere it's 1. Well, it's first of all, these guys are all not unit vectors, so you may have to multiply by 1 by root 2 or something, but that will come to later. So if you do 1 1 1 1 1 all the way till 1, then it won't satisfy this guy. So up to n minus 1 you make 1, the last one you can make it as minus n minus 1, right? Do you see this? So this one will have this will belong to S, right? Because if you add up all these guys, you get 0, right? So it's okay. But interesting thing is, so supposing I call it let's call it U1. U1 I've been using for W1. Okay, W1, W2, Wn minus 1. Okay. So interesting thing is v dot v inner product v comma W1 will be 0. Okay. So on till inner product v comma Wn minus 2, right? All of these guys are 0. So v is orthogonal to all of these fellows. So maybe that's a bit interesting, but then all of these guys are not orthogonal to each other, right? So it's not clear how Gram-Schmidt will efficiently work here. So you can think about it. So you can do a Gram-Schmidt if you like. You will get some basis, and then you can try to find out. All of that seems frighteningly complicated. Maybe there has to be a simpler method. We'll come back and revisit this problem a little bit later, but just think about problems like this. When you have a large dimension, guys, and you're trying to project onto that, it seems like the Gram-Schmidt and the definition of U1 Hermitian is a bit painful to operate. So even though you can find some vectors like this perpendicular, it's not quite working out to be in a simple way. So maybe we need some simpler methods to tackle this, maybe some more systematic methods to look at projection and S-parp or all that. But anyway, nevertheless, at least for this problem, you know how to try it directly. Okay, so that concludes our view of orthogonal complements. and projection. Thank you very much.